Okay, and on that note, we move on to the next lecture. We now have 3 lectures about TG51, starting from an overview of the protocol itself, which hopefully most people are familiar with, but we're going to start with the basics. Then Dave Followell is going to talk about some more clinical aspects of the implementation that RPC is familiar with, and then I'll have a talk about the physics in TG51. So on that note, we'll turn it over to Saiful.
Thanks, Dave. I actually want to take this opportunity to thank our co-directors for this summer school, Dave Rogers and Joanna Sigler, for inviting me to participate in this. Actually, it turned out to be already very exciting summer school. I feel like I've learned a lot yesterday, lots of equations, and tried to absorb a lot of the beer time. It was actually quite fun. So, Dave asked me to give an overview of TG51, and as he just mentioned, there are 3 talks back to back. I'll provide an overview of the TG51 protocol, and then this will be followed by all the different problems that you encounter when you're going to implement TG51 protocol in the clinic. And then they will tell us all the physics behind everything that went into TG51 protocol. Before I start, I just wanted to get an idea. Is there anyone in the audience who is not using TG51? That's the main one of the authors. So that's good. So that's good. So everybody is quite familiar. So this will be an overview for all of you. Here is an outline of my presentation. Just a slide on the background of why we went to TG51. Then I'll describe the basic equations in TG51, step-by-step procedures for photon and electron beam calibration, and then what to do, what did the protocol recommend with the chambers that have not been included in TG51. Some errors identified in TG51, followed by conclusion. So during the last 3 decades, AAPM has recommended 3 generations of protocols. In the late 60s, it was the SCRAD, followed by TG21 in the early 80s. And these protocols were based on the use of an ionization chamber calibrated in terms of exposure in a standard laboratory's cobalt-60 gamma ray beam. TG51 was published in 1999. The task group actually was formed in 1991. It took 8 years. This protocol is based on the use of an ionization chamber calibrated in terms of absorbed dose to water in a standard laboratory's reference quality beam. And this absorbed dose coefficient is denoted by NDW. These are the authors of the protocol. Peter Ullman is the chair. I see him in the audience. And one of the other authors, Dave Rogers, is also in the audience. Authors who are not in the audience are Peter Biggs, Bart Kersey, Will Hansen, and Ravi Nath. So I'll show 2 slides, start summarizing actually all the different steps that are needed to calibrate photon and electron beams. So I'll start with summary that will set the ground for really talking about the details of what is included in the protocol. For photon beams, that's the equation that's given in the protocol. dWq is the dose to water at a reference depth in water in a user beam of quality Q. And dW cobalt-60 is the absorbed dose to water calibration coefficient in a cobalt-60 beam obtained from the ADCLs. KQ is a beam quality conversion factor, and I'll talk about that in details later. And M is the charge reading. So the first thing when you're ready to calibrate your 6 MV or 18 MV beam or an electron beam, we're talking about photons here, what you do is select your ionization chamber. Then you need to get NdW cobalt 60 for your chamber. What you do is send it to an ADCL. And they provide you an NdW cobalt 60 for your chamber. The other factor is KQ. The protocol provides KQ as a function of beam quality. So that means that you have to measure beam quality. And once you have measured beam quality, the protocol gives in a graphical form or in a tabulated form the values of KQ as a function of the beam quality for various cylindrical chambers. The only thing left is now to measure M, and you measure M under reference conditions, and there are a lot of steps that one has to go through to get a corrected value of M. So once you've done that, you've essentially determined the absorbed dose to water at the reference depth. So these are all the different steps. One slide summarizes it all for photon beam calibration. The next one is, this slide is for a summary for electron beams. Again, it's a little bit of complicated equation. There are different factors, and I'll talk about that later. So this is what you get for your chamber. First step is you identify your chamber, send it to ADCL, get an NdW, cobalt 60, and then the protocol provides calculated values of KQ for various cylindrical and plane parallel chamber. And for each chamber, there is a specific value for it. So it's a table lookup. This factor, this is a photon electron conversion factor. This is an electron quality conversion factor. It is given as a function of beam quality. So you need to measure beam quality. Protocol tells you how to do that. And once you have measured beam quality, then the protocol gives you the values of KR50 prime as a function of the beam quality for various cylindrical and plane parallel chamber. You need to measure the gradient correction factor P gradient Q. Protocol tells you how to do that. Measure charge, and then you have determined dose in an electron beam. So that's the summary for electron beam calibration. So that as the background, so I'll now spend the rest of the talk discussing some of the details of how to go through that. But before that, just a couple of words as to why did we move on to an absorbed dose to water-based calibration formalism. There has been a lot of discussion about that in the literature. I'll not spend my time on that, but I'll just say that it's a much simpler formalism than an NK-based formalism. For example, if you have a NdW calibration for your ionization chamber in a beam quality of interest, for example, you're calibrating a 6 MV beam or an 18 MV beam. So if you have an NdW calibration for a 6 MV or an 18 MV obtained from the standards laboratory, really then all you need is this equation. You don't need anything else to calibrate your beam. Everything that we heard all day yesterday, all the correction factors and everything, will not need any of those. It becomes as simple as that. I was having a little discussion with Dave at beer time. He pointed out, flattening filter free versus flattening filter based. We need to look at those. But right now, we really don't have, except maybe 2 accelerators that are sold that Dave mentioned, which are flattening filter free. Almost all our accelerators have flattening filters. So if we can obtain these calibration coefficients, I probably am interchanging calibration factor and calibration coefficient, still trying to catch up to this new terminology. So if our primary standard slabs, NIST provides us NdWq as a function of beam quality for photon and electron beams. Life is simple. There are various standard labs in Europe who provides these calibration coefficients for both photon and electron beams as a function of beam quality. I know NIST is, they have an accelerator, they are working towards it, and when the time comes when we get accelerator-based calibration, then application of the protocol using an NdW-based formalism is very simple. Now, until we have NdW calibration in accelerator beam quality, right now what we have is cobalt-60 machines at the ADCLs, and they're the ones who are providing NdWq calibration at cobalt-60. So when the calibration measurements are done at a cobalt-60 beam, but you want to calibrate your beam at 6 MV or 18 MV or electron beams, then this is the dose equation that is used for the determination of dose. Kq is a factor that accounts for the effects of the differences between this cobalt-60 beam and your 6 or 18 MV beam. It's chamber specific. It depends on the beam quality, and it converts NdW cobalt-60 into NdWq. So the dose equation simply becomes M times NdWq. The beam quality factor Kq, by definition, is given as the ratio at the qualities Q and cobalt-60 of the absorbed dose to water calibration coefficients of an ionization chamber. As I mentioned, ideally, this should be measured directly for the user's ion chamber for the user's quality. But that's not available. As I mentioned, only a few primary standard labs can do these measurements. So in the absence of that, the other alternative is to provide calculated values of Kq. And this is what TG51 has done, provided calculated values of Kq for many cylindrical and plane parallel chambers. Kq is given by this expression. It's a ratio at the qualities Q, beam quality of interest, to cobalt-60 of the water-to-air stopping power ratios and the various perturbation factors. We've spent all day yesterday understanding how to calculate some of these perturbation factors as a function of beam quality, and I'm sure Dave will spend a significant portion of his time telling us how some of these calculations were done for the data presented given in the protocol. Okay, so the basic equations for TG51. You have already seen these equations. It's the photon beam equation. The protocol has provided calculated values of Kq for cylindrical chambers only, and recommended that only cylindrical chambers are allowed for use for calibration for photon beams. You can use a plane parallel chamber in a cobalt-60 beam if you have a calibration coefficient for a plane parallel chamber in a cobalt-60 beam. The reason plane parallel chambers were not recommended for use in photon beam is that information was not available for wall correction factors for plane parallel chambers at these high energy beams. The calculation for the dose equation for electron beam is a bit complex. Here, Kq is broken down into three components. Kcal, which is the photon-electron conversion factor, which converts the absorbed dose to this NdW at cobalt-60, the calibration coefficient, to that NdW at an arbitrary beam of quality QE cal. And it has a fixed value for a chamber. So this product essentially becomes an NdW QE cal. This electron quality conversion factor, it's a function of beam quality, which is identified by this. R50 is the beam quality, and I'll talk about that soon. So this electron quality conversion factor converts NdW QE cal into NdW Q. P gradient Q, there was a good bit of discussion about it yesterday. It's a gradient correction. It depends on the radius of the chamber cavity, the ionization gradient at the point of measurement, and it must be measured by you. And protocol gives a recipe for how to measure that. The photon electron conversion factor K cal is given by a ratio of these. It's again water to air stopping power ratio, perturbation factors, evaluated at the beam quality. It's an arbitrary beam quality QE cal with an R50 of 7.5 centimeter, and at cobalt 60. These are two different modalities of the, and this is electron beam, this is a photon beam. Notice here, in the denominator, there is this P gradient that's there. Yesterday you heard P repel, P replacement. P replacement really is a product of these two terms, P gradient and P fluence. So the gradient effect, the term gradient, P gradient has been taken out of this, and it's in the main equation for the dose equation. So for every chamber at a given beam quality, all of these have a fixed value. So the K cal for a given chamber is unique. The reason for introducing this K cal into the formalism was that it made the data analysis much simpler, in terms of introducing this arbitrary beam quality QE cal. And then also, this quantity can be measured directly when the primary standards for absorbed dose water in electron beam is available. And then also, as you'll see later on, the protocol recommended that for electron beam calibration, you use a plane parallel chamber. It's because there has been some studies that have shown that the response of a plane parallel chamber depends, it gets significantly affected by the construction of the constructional details of the chamber, and its response in a cobalt 60 beam becomes very different depending upon the construction. So the protocol recommended that you cross-calibrate a plane parallel chamber against a calibrated cylindrical ionization chamber as the preferred method. The electron quality conversion factor is evaluated at the beam quality of interest, Bolivar electron beams, 6 MeV to 20 MeV, to the arbitrary electron beam quality QE cal. It's a fixed beam quality. And it's a ratio of water to air stopping power ratio and the various perturbation factors. Larry has given a nice presentation about what a well-guarded chamber is. And for a well-guarded chamber, the protocol assumed that all of these factors are 1. The wall correction factor is 1. The fluence correction factor is 1. Plane parallel chambers don't have central electrode. So for a well-guarded chamber, this KR50 prime essentially becomes a ratio of water to air stopping power ratios at the beam quality of interest and to QE cal. So it essentially becomes for all well-guarded chamber, you get the same curve, the same value as a function of beam quality. There are a couple of chambers in the protocol. I'll show it later on, the Marcus chamber and Kapintech chamber. Those were not well guarded, so they had a value of the fluence corrections, and so there are two separate curves for KR50 prime that were calculated for those two chambers. For cylindrical chambers, there was much discussion about the fluence correction factor yesterday. Alan Nahum showed us that these correction factors at low energies can be up to about 5% or so, depending upon the chamber volume. And so for different cylindrical chambers, the KR50 prime curve as a function of R50 is different. But the chamber-to-chamber variation really is much small, and it's because of the introduction of the KE-cal factor. Okay, so let's talk about now, move on and talk about the step-by-step procedure for the clinical implementation of TG51 protocol. Start with photon beams. The basic starting point is our equation. And the first step, obviously, is after you have decided which chamber you want to use, you send your chamber to an accredited dosimetry calibration laboratory to obtain your NDW cobalt 60, that calibration coefficient. There was a good bit of discussion about a few minutes ago how chambers can get messed up during transit, what UPS can do. So it's important to perform stability checks of your chambers before you send the chamber out to the calibration laboratory, and repeat the same after you receive the chamber. This is just to ensure that the chamber characteristics has not changed during the transit, so that the calibration coefficient that you have obtained or the calibration laboratory has provided for your chamber is applicable. And NDW must be traceable to the national primary standards of absorbed dose to water to maintain the uniformity of the symmetry. So what happens when you send your chamber to Wisconsin ADCL or MD Anderson ADCL or KNS ADCL? What they do is they go through different steps. The Cal labs, they have established the absorbed dose to water at a reference depth, 5 centimeter, in a water phantom for a cobalt 60 beam by going through different procedures with comparison with NIST and many other means. So after you have sent your chamber, they place your chamber, the point of measurement of the chamber at that reference depth. I'll come to point of measurement in a bit. And then you radiate the chamber for a certain amount of time and get a charge reading. The NDW cobalt 60 is then obtained from the dose that they already know at the point of measurement divided by the charge reading, corrected for the various influence quantities that influence the charge readings, just to give it to, refer to standard reference conditions. So this is what they do. They send your chamber back with that calibration coefficient. Now you're ready to calibrate your own beam in your hospital. What you do is you use that chamber and place that chamber at a reference depth under reference conditions recommended in the protocol, radiate it, get a charge reading, MRAW, correct it for the various influence quantities, and you obtain a dose at a point when the chamber is removed. That brings us to the discussion of point of measurement. For cylindrical chamber, the point of measurement is defined to be on the central axis of the chamber at the center of the active volume of the cavity. So it's for any 2571 chamber, it's really 13 millimeter from the tip of the chamber, of the thimble. For a plane parallel chamber, the point of measurement is really at the center of the front surface of this air cavity. That brings us again to the concept of effective point of measurement, and that concept is important because it's used for the measurement of beam quality, and again, there has been a lot of discussion about it yesterday. So what happens when a chamber with a cavity is placed in a medium? Alan Nahum told us yesterday that there are two effects that take place. Perturbation by the cavity of the electron fluence that enters the cavity, and that is accounted for by the fluence correction factor. And the other one is when you place a chamber, position a chamber with a center at a given depth, the chamber samples an electron fluence that is different from the electron fluence that is present at that reference depth in an undisturbed medium. And that is what we correct by using the gradient correction factor, and Alan showed some nice graphs for that. So this gradient correction factor in the KQ calculation is explicitly included in the KQ calculation for electron beam. It is taken out of KQ, and it gives rise to an effective point of measurement, which is obtained by displacing the chambers towards the radiation source by a fixed amount. For a photon beam, this fixed amount, this distance dc, is equal to 0.6 times the radius of the cylindrical chamber cavity, and for electron beams, it is 0.5 times our cylinder. For plane parallel chambers, the chambers are designed such that the chamber samples electron fluence that enters through the front window. The electron fluence that enters through the side of the window for a well-guarded chamber is negligible. So the effective point of measurement for a plane parallel chamber is really at this point. People who are very anal about the thickness of the chambers, some of these chambers have a thickness like of the order of a millimeter, so they worry about these thicknesses when they try to set it up when they're doing calibration measurements. So Larry has spent a lot of time talking about some of the correction factors. I'll come to that. For chambers, the recommendation of the protocol is that all measurements must be performed in a water phantom. And plastic phantoms, including water equivalent plastics, are not allowed for various reasons. But you can use a plastic phantom for routine quality assurance checks, provided you have established a transfer factor for measurements in the plastic phantom during calibration. You calibrated your beam, put in a plastic phantom, put in a detector. For certain monitor units, you have a reading. From then on, you can use that to measure, say, for example, the constancy of the output of the machine. So all measurements are to be made in a water phantom, so the chamber must be waterproof. The ideal condition is if the chamber is waterproof, and if it is not, you can use a PMMA sleeve, thickness less than a millimeter, and such that the air gap near the chamber wall and the PMMA sleeve is less than 0.2 of a millimeter. The protocol cautions against using a latex rubber sleeve. You can use that, but these tend to have powder in that, and there are studies that shows that the response of the chamber can be affected by the presence of the powder. The chamber reading, AMRO, is affected by various parameters. Larry has mentioned some of that. The it's actually affected by many influence quantities. The influence quantities are quantities that are not the subject of interest, but that impact the quantity that we are measuring. The calibration coefficient that we obtain for an ionization chamber is only valid for the reference conditions for which it applies. Now, in the clinic, the measurements that we do, those conditions are different from the calibration conditions. So we need to apply the appropriate correction factors so that they can be referred to the calibration conditions. So these are some of the various correction factors. Larry's PTP was backwards. In this case, fortunately, it's forward the right way. For vented chambers, we know that the mass of the air inside the cavity is subject to atmospheric variation. So we need to apply a temperature pressure correction to convert the ambient air mass to that of the reference condition. And that's the equation that is used for that temperature pressure correction. You must investigate the effect on the chamber reading, the application of polarizing potential of opposite polarity. In photon beams, the polarity effect is, or its variation with beam quality is usually negligible. But in electron beams, there is significant polarity effect, particularly for parallel plate chambers at low energies. The corrections for polarity effect is obtained by taking measurements with both polarities, and the protocol recommends this equation for polarity effect. M rho plus is the reading when positive charge is collected, and Larry tried to say very nicely how reading positive charge versus negative charge. M rho minus is the reading when negative charge is collected, and M rho is the reading, either M rho plus or M rho minus, depending upon the calibration geometry. And that polarity should correspond to the polarity that for which you have obtained the calibration coefficient for your chamber. So if the ADCL provides a calibration coefficient for they will say at which polarity they have provided it, positive or negative. Then when you do your calibration measurement, you should do the calibration measurement using the same polarity. So it's important that you read your calibration certificate for that. And the signs of M rho must be used. Usually they are of opposite signs unless the background is very large. After you change polarity, allow enough time for the reading to stabilize. Otherwise, you will end up with an error that can be much larger than the error you're trying to correct for. Recombination correction. Again, Larry spent a good bit of time talking about it. The incomplete collection of charge inside the cavity gives rise to this correction. And it's given by p-ion. Larry mentioned that there is general recombination or initial recombination that takes place inside the cavity, and the protocol recommended the 2-voltage technique for correcting for this ion collection efficiency. Here, VH is the normal operating voltage that you'll use to calibrate your beam, and M rho H is the reading corresponding to this high voltage, this normal operating voltage. VL is the lower voltage, reduced by a factor of 2 or more, and M rho L is the reading corresponding to that. Once you have that, the p-ion for pulsed beam or pulse swept beams are given by this equation. The protocol cautions that if you have an ionization chamber that has a p-ion value of greater than 1.05, you should use a different chamber because the uncertainties in the value of p ion becomes much larger. And also you shouldn't just try to raise the voltage and try to reduce the value of p ion, because the assumptions that are used in the basic theory for the calculation starts to break down. Electrometer correction factor: when you send your chamber and electrometer to an ADCL, they provide you calibration factors for the chamber and electrometer. They can provide it separately. For chamber, it's given, and it's gray per coulomb. And then for the chamber, they give gray per coulomb, and for the electrometer, they can give it a coulomb per reading, nanocoulomb per reading, or depending upon the readout of the electrometer as a dimensionless quantity. And it is unity if the chamber and electrometer are calibrated as a unit. Some practical considerations: make sure that you check the stability of the entire dosimeter system, check the integrity of the waterproofing sleeve, allow enough time for the dosimeter to reach thermal equilibrium with its surroundings. Larry emphasized the importance of charge equilibrium in the different materials in cable and others. So I have found myself that whenever I change polarity or something, if I give a whopping dose of 2 to 5 gray, then I don't have to wait. All my readings are fairly well reproducible. That's my personal experience. Make sure that after you switch polarity or the polarizing voltage, as I mentioned, allow enough time so that the chamber reading reaches an equilibrium, and the leakage current should be insignificant. So we talked about NDW, we talked about charge measurement, and the next thing we need for determination of dose is beam quality KQ. The beam quality conversion factor KQ. And as I mentioned early, KQ is given as a function of beam quality. That's the expression we have seen. So we need to measure beam quality. So what is beam quality? For photon beams, the beam quality is specified as a percentage depth dose at 10 cm depth in water due to photons only, excluding electron contamination. So the beam quality is percentage depth dose 10, and this little x is very important. That x indicates that this is a percentage depth dose with electron contamination removed. So we need to measure percentage depth dose. We all thought that measurement of percentage depth dose is easy. Actually, it's quite complex. And I'll say a word or two as to why that is. When we measure in a clinic, we set up our water tank, we have our chamber, we scan it, we get a curve in the computer monitor. What we see there is a percent depth ionization at different depth. And that assumes the point of measurement of the chamber is as I described earlier, at the center of the chamber on the central axis, at the center of the active volume. So that's the curve you see, that's your percent depth ionization curve. To convert it to dose, there are many factors that are needed. You need to multiply these readings with P-ripple. We saw yesterday how some of these factors, P-ripple, which is P gradient, P fluence, P wall, P central electrode, these are all the factors, P ion, P polarity. So we need to know all these values of all these parameters as a function of depth so that we can calculate the dose at different depths divided by dose at D max, then we get percentage depth dose. And Jan has shown us how some of the recent calculation shows how P central electrode and P wall changes as a function of depth. So the protocol assumed that almost all of these factors as a function of depth is negligible. you account for the gradient correction factor only by shifting the percent depth ionization curve towards the source by 0.6 R. For plane parallel chambers, no shift is needed because of the location of the effective point of measurement. So what I just described is when we get a scan using a cylindrical chamber, this is the curve that we get. And then there are softwares in the scanning system. They allow you to shift the curve towards the source by 0.6 R. And when you have shifted that, this is the curve that you get. With all the assumptions that I just mentioned taken place, assuming that they all hold true, including the water-to-air stopping power ratio, and Alan has shown as a curve that shows that the variation of the stopping power ratio for photon beam beyond Dmax is also very negligible, less than 0.1%. Then this curve essentially is a depth dose curve. Then you go to 10 cm depth, read off of the graph what the percentage depth dose is for your photon beam. This beam quality, this percentage depth dose, must be measured for a certain geometry. Your SSD should be 100 centimeter. Field size should be 10 by 10 centimeter at the phantom surface. It's because the KQ factors, all these equations for P wall, P central electrode, all those, they have been calculated for different beam qualities as a function for this particular geometry. And as we know, if you change the field size, for example, change the SSD, or percentage depth dose changes. Since KQ has been calculated for this specific geometry, the beam quality must be measured for this geometry. The other thing is, we know that when the beam energy goes higher, for beam energy less greater than 10 MV, the electron contamination becomes important. And that electron contamination affects the value, percentage depth dose, and Dmax, and that in turn affects the value of percentage depth dose at 10 cm depth. Our beam quality for photon beam is for pure photon only. So to account for that electron contamination effect, the protocol recommends that you put a 1 millimeter lead filter for 10 MV or higher beam at a certain distance from the phantom surface, 50 centimeter, and if the clearance does not allow. I see Dave is standing up. That scares me. Ooh. Okay. So I gotta regroup myself. Okay. And what that does, as I'm regrouping, so there is a lot of electron contamination that is produced at the machine head. This lead filter essentially removes these electrons. But what that lead filter does is produces some additional electrons, and the protocol gives you equations to account for these additional electrons that are produced from the lead. So there's a correction for lead foil. There are different equations that the protocol gives you. You measure the percentage depth dose with the lead in place and use this equation to get the percentage depth dose with photon, with the electron contamination removed. And you should use the values of percentage depth dose in this equation, not fractional depth dose. Once you have done that, then you have measured the beam quality. KQ is now given as a function of beam quality for different chambers. You have measured beam quality. Now you're ready to calibrate your beam. The first thing you do is remove the lead filter. You don't want to keep that in the path of the beam. And these are the reference conditions. You place your chamber at 10 cm depth, 10 by 10 field size. You can use SSD or SAD technique and get your charge rating, plug in all the values in the equation, you get the dose at 10 cm depth. And if you want to get the dose at Dmax For an SSD setup, you use the clinical PDD curve. And for an SAD setup, you use the TMR. No need for, can I take another 5 minutes? I'll quickly go through electrons. I thought we had coffee time between now and then. Okay. Okay, all right. That's the basic equation. We talked about KR50 prime. It's given as a function of beam quality, so we need to measure beam quality. For electron beam, the beam quality is defined by half R50, which is the depth in water at which the absorbed dose reaches 50% of its maximum value. Using a cylindrical chamber, you measure depth ionization curve, shifted by 0.5 R. That's your gradient corrected depth ionization curve. From there, and it also must be measured under these reference conditions, 100 SSD field size, 10 by 10 or 20 by 20 if the beam energy is greater than 20 MeV or 50 greater than 8.5 centimeter. You get a gradient corrected depth ionization curve. You go to the level of 50%, get a value of I50. Protocol gives you equations to calculate R50 from I50. And protocol gives you a reference depth, which is dref, which is not necessarily the depth of Dmax. So if you are calibrating at the reference depth and you want to go to Dmax, you need to get a percentage depth dose curve. And the depth dose curve is obtained from the depth ionization curve by multiplying the water to air stopping power ratio and other perturbation factors. R50 from I50, you have seen that equation since most of you are familiar with the protocol. Once they are all done, we have measured the beam quality for different beams. KR50 prime is given as a function of beam quality for various cylindrical chamber. For plane parallel chamber, as I mentioned, for all well-guarded chamber, there's only one curve. For Marcus and Kapintec, they're different because they're not well-guarded. Protocol tells you that for energies less than 6 MeV, you must use a plane parallel chamber. No cylindrical chambers are allowed. As I mentioned, only water phantoms are allowed. But for energies less than 10 MeV, it recommends that you can use both cylindrical and plane parallel chambers. At higher energy, both cylindrical and plane parallel chambers are recommended. Reference depth is given by a factor here, an equation. We heard about that yesterday, how one arrived at this equation. It's usually close to Dmax for less than 10 MeV, deeper than Dmax for E0. These are the reference condition you have seen that in the protocol. And then the last thing here is P gradient Q. You need to measure that. Here's the recipe. You place the point of measurement of the chamber at the depth of dref plus 0.5 R, divided by that for charge reading at dref. Take the ratio. That gives you P gradient. I will not get into cross-calibration because of time. So the protocol tells you really, if you read the last two sections, what to do with chambers that are not included in the protocol. Actually, Jan Sundsen has a task group who are looking at some of the new chambers that are in the market that have not been included in the protocol, and they'll be providing values for KQ for those. TG51 simplifies clinical reference to symmetry. It also improves the accuracy of clinical reference to symmetry. Thank you.